Thanks to the organizers for this very nice conference. This talk is based on joint work with Artur Avila, Giovanni Forni, and Corinna Ulcigrai. And it's about ergodic properties of time changes of Nilflows. So maybe I should start by telling you or reminding you what Nilflows are. The simplest class of Nilflows are the so-called Heisenberg Nilflows. And they are defined as follows. You consider H the three-dimensional Heisenberg group, which is just the group of 3x3 upper triangular unipotent matrices. And you fix any lattice in H, for example, the discrete subgroup of matrices of the same form, but with integer entries. And the quotient H mod gamma is what is called the Heisenberg nilmanifold. And this is a smooth three-dimensional manifold that you could see, for example, as a circle bundle over a two-dimensional torus. I'll come back to this in a second. So this is the phase space of the Heisenberg Nilflow, of any Heisenberg Nilflow, which are defined by fixing any element of the Lie algebra of H. So in this case, it's just 3x3 strictly upper triangular matrices. Any such element generates a one-parameter subgroup by exponentiating. And the Heisenberg Nilflow is just the restriction of the right multiplication to this one-parameter subgroup. So explicitly, you could write, you fix any point in your Heisenberg nilmanifold, and you just multiply on the right by this matrix, if I've done the computations correctly. More in general, a Nilflow is given by fixing a simply connected nilpotent group, and the lattice in G. The quotient G mod gamma is what is called the nilmanifold, and it's always compact. So there are, for nilpotent groups, being compact is equivalent to being finite volume. And the Nilflow is generated by fixing any non-zero element in the Lie algebra, and is given by, again, the restriction of to the one-parameter subgroup generated by X of the right multiplication, map. So these are the flows we are interested in. Well, not quite. And the first observation is that this flow preserves a smooth measure, which is the measured induced on M by the R measure on the nilpotent group. So we have a smooth flow and a smooth manifold. We have a smooth invariant measure. We can ask about the ergodic properties of these flows. And the first observation.
Give some simplest examples.
So you could always, so in the case of the Heisenberg, okay, if I should have said a nilpotent non-abelian group, otherwise it's just a torus, and it's just a linear flow on a torus. The simplest class of examples are these Heisenberg Nilflows that I given before. And I'll describe a bit better what I mean by a circle extension over a torus, but a nilmanifold you could always see as circle extensions or toral extensions over some nilmanifold of lower dimension and lower step. So the first observation about the ergodic properties of this flow is that they always have a very special factor, which is given by the algebraic properties of the nilpotent groups. In particular, by definition, the quotient of the group by the derived subgroup is always a non-trivial abelian group, which is simply connected. So it's isomorphic to R to the n for some n, so that when you quotient by your lattice, you get some high-dimensional torus. And the projection on this quotient induces actually a factor of your Nilflow, which as a factor a linear flow on a torus. So for example, in the case of the Heisenberg group we've seen before, the derived subgroup is just the center of the nilpotent group, which is just this one-dimensional subgroup, so that when you quotient by this one-dimensional subgroup, essentially you are left with these two coordinates. And if this guy is the generator of your Nilflows, so you're killing whatever was happening in this component, and what you see is just a linear flow in direction xy. And the quotient manifold in this case is actually just isomorphic to the standard torus. This is an easy observation, but already it's telling you something about the properties of the Nilflows. In particular, Nilflows are never weakly mixing. Why? Because linear flows on tori have lots of non-trivial eigenfunctions, and you can just consider the pullback to your Nil manifold, and you have non-trivial eigenfunctions for the Nilflow. It's also a classical result by Auslander, Green, and Hahn that to determine whether your Nilflow is uniquely ergodic, it is enough to look at the projected linear flow. So if the linear flow on the torus is minimal or ergodic or uniquely ergodic, then also your Nilflow is uniquely ergodic. On the other hand, it's also another classical result by Green. Although Nilflows are never weak mixing, they are mixing and they actually have the back spectrum on all the functions that lie in the orthogonal complement to the pullbacks of functions that live on the torus. So what this result is suggesting us is that although they are never weak mixing, the only obstruction to mixing is the presence of this toral factor. And if we are able to destroy this toral factor, maybe we can see mixing. So this is a bit the heuristic. Before going to the result, let me put this in context of smooth dynamics. So these are examples of homogeneous flows, but if we forget about the homogeneous traction, I would just look at them as smooth flows. Nilflows are examples of what are called parabolic flows. So flows for which the divergence of nearby points is polynomial in time. So one way of encapsulating this vague notion into a more formal definition, for me, smooth flow is parabolic if you look at the differential of the time t map, and this grows as a polynomial in t. So this is in sharp contrast to what we've seen today about hyperbolic flows. But still, these classes of flows contain some interesting examples. For example, other examples of smooth parabolic flows are area-preserving flows on higher-genus surfaces. So in this case, the divergence is given by the presence of singularities that will tell you that points will split up after some time. Or cycle flows on negatively curved, on the unitangent bundle of negatively curved manifolds, or more in general, of unipotent flows on quotients of semi-simple Lie groups, which probably we'll hear more next week. However, I should point out that there is no general theory for smooth parabolic flows, and only some very few cases are well understood. And for example, unipotent flows or cycle flows are examples of homogeneous flows for which we can exploit powerful algebraic and representation theory machinery to study them. But when we perturb them in a way that we still have a smooth parabolic flow, but the symmetries of the systems are destroyed, well, very little is known in this case. So one reason to study smooth perturbations of these homogeneous flows for me is to answer two kind of natural questions, which are which properties are typical for a smooth parabolic flow. So if typical parabolic flows, which are the ergodic properties? And on the other hand, can we identify some mechanisms that are responsible for some chaotic properties for parabolic flows that are, in some sense, robust to smooth perturbations? This is why we want to study smooth perturbations, and the simplest class of smooth perturbations are what are called time changes. So in general, the time change of a smooth flow induced by a vector field x is given by choosing a strictly positive function and considering the flow generated by the vector field alpha x. So I'm just rescaling in a non-constant way your vector field. So I'm not changing the global orbit structures of the flow, I'm just changing the way I parameterize the time on each orbit. And you can write some formula that express your time change in terms of your original flow and this additive cocycle. And easy observation is that if your smooth flow was preserving some volume form omega, then the time change flow preserves an equivalent volume form. And since orbits are not changed, ergodicity is preserved by performing a smooth time change. On the other hand, mixing is more delicate. and requires some more thinking. And in the case of the Eurocycle flow, mixing and spectral properties have been investigated, starting from Marcus, who exploited a form of shearing mechanism to prove mixing for Eurocycle flows on non-constant negative curved manifolds. And for the Eurocycle flow, this shearing mechanism is simply by taking some short geodesic segment and flowing it by the Eurocycle flow. And what you see is that this segment gets sheared along the Eurocycle flow direction, and for large enough t, becomes very close to a long segment of an Eurocycle orbit. So since you know that the Eurocycle flow is ergodic or uniquely ergodic in the compact case, these sheared segments become equidistributed. So you can prove mixing by this shearing plus ergodicity argument. And this shearing mechanism is a geometric, in some sense, robust mechanism that we will exploit also in our setting. One more definition, some time changes behaves like a constant time change, so in some sense are trivial, and these are given by homologous time changes. So we say that two functions are homologous if their difference can be expressed as the derivative along the flow. And it's an easy exercise to say that, to see that if your time change is given by, here I'm taking 1 over alpha for making the statement easier to read, but so if your time change is given by a function which is homologous to the constant 1, then the two flows are isomorphic. So in some sense, we want to rule out these trivial cases and investigate the properties of time changes induced by non-trivial time change functions. So let's go back to our Nilflows. Recall that they were not weak mixing because they had this algebraic obstruction of a factor which was isomorphic to a linear flow on a torus. But what happens when you perform a time change? And Avila, Forni, and Ulcigrai proved that in the Heisenberg case, for a generic set of functions which you should think of them as trigonometric polynomial, and if I have time, I say something more, otherwise not. Any positive function induces a mixing time change if and only if it's not homologous to a constant. So again, as soon as you perform a non-trivial perturbation, you destroy this toral factor, which was your obstruction to mixing, and you actually see a mixing flow. And in the Heisenberg case, this condition can be checked explicitly. Later, I generalized this result to a specific class of higher step nilpotent group. And the main result of this talk is that the same phenomenon happens for every uniquely ergodic Nilflow on any nilmanifold. Namely, for any uniquely ergodic Nilflow on a nilmanifold, and for a set of functions on your nilmanifold, which you should think of them as trigonometric polynomials, then within this set, any positive function which is not homologous to a constant induces a mixing time change. So again, maybe the takeaway of this result is that generic time changes are mixing, so this algebraic obstruction to mixes is very fragile and sensitive to perturbations. And also, a shearing mechanism, you can, in some sense, use a robust shearing mechanism to prove mixing for at least this class of smooth parabolic flows. Okay, yeah, you have some more time, so I can say a few words about the proof. So let me give a brief sketch of the proof. Let's consider our generator of the Nilflow and the time change induced by 1 over alpha. And for simplicity, let me assume that we can find two other vector fields, y and z, such that z is contained in the center. So here n stands for the step of nilpotence of the group. So this is the last term in the central descending series, such that x commuted with y give you z, and let me also assume for simplicity that the exponential of z is in your lattice. So what does this mean? So z is an element in the center, so its action, since also it belongs to the lattice, it the action of the one-parameter subgroup generated by Z on M descends to a circle action. So I can decompose the L2 spaces into Fourier modes. And so this is what I meant by trigonometric polynomial. And the trigonometric polynomial with respect to this element Z is just any finite sum with respect to this decomposition. So the first step is we write our time change function as a sum of one component that lies in the zero Fourier mode, which is just the functions which are invariant by Z. In particular, you could see them as pullback of functions that live on the nil manifold given by the quotient by the action of Z, and everything else. So the proof is divided in two cases, depending whether this component is a coboundary or not with respect to the generator of the Nilflow. And why do we do this? Well, because we want to use an argument of mixing via shearing. So I want to see that when I take a short segment in direction Z and I push it via the flow, this segment becomes sheared along the direction of my flow. So if I compute the Lie brackets between my time change and Z, this is an easy computation, but this is telling you the infinitesimal shear in the direction when I push my vector field Z by my dynamics. And when you integrate this system of ODEs, if you want, you get an explicit expression for the push forward of Z by the dynamics of the flow. And this is a component of the same length in direction Z plus this term in the direction of the Nilflow. So I could have two cases. If this component is a coboundary with respect to X, then the derivative with respect to Z, which is also equal to the derivative of alpha with respect to Z, since the difference of the two is invariant by Z, is a coboundary with respect to X. So this function is a coboundary with respect to X tilde. So this term is globally uniformly bounded. So I see no shearing. But in this case, you can actually prove that your Nilflow projects onto a Nilflow, on a time change of a Nilflow on a quotient manifold. You can assume by induction that the projected Nilflow is mixing, and you just have to lift mixing to the original nil manifold by wrapping in the fiber argument, which I'm not gonna explain more, but you can ask me more if you want. On the other hand, if alpha perpendicular is not a coboundary with respect to X, then this function, actually you can prove that grows in averaging measure by a standard Ghosh-Edlund argument. And then you have to exploit the properties of alpha being a trigonometric polynomial, and this is one of the key reasons why we needed to, I'm done, to restrict to this setting to prove that this function actually grows in measure. And then you can prove by a mixing via shearing argument that this sheared segment becomes equidistributed, and then you get mixing. So I'll stop here. Thank you.